Hello everyone, and once again warm welcome to one of other presentations that I want to do today. It's been a bit of a long pause I've had ever since I posted my last presentation on this platform, and that's simply due to having a very busy work schedule and not having enough ground time to uh, produce some of these educational material that I like doing. Nonetheless, today we will talk about performance, and this series will be divided into a couple of parts. I don't know how many, but it won't be maybe more than 10. And in each part, we'll be looking at how to calculate the various aspects that determine a safe takeoff of an aircraft, especially of the Dash 8 Q400, which all of my series for now are based on, since I am the one who flies. I'm one of the pilots on this fleet of aircraft currently. So without further ado, we'll just go into discussing what we're going to do in this presentation of ours. So what we will discuss will be how to determine the maximum takeoff weight based on the conditions of the day. And in this particular point, the conditions mainly focus on the temperature for now. So temperature will be our main concern to work out the takeoff weight, maximum takeoff weight we can carry. And there's something called runway analysis charts. Those are performance tables that are produced by the manufacturer, and they also cater for different airlines, depending on if the airlines are using such tables or they're using electronic means. In many companies, or in some of the companies, including the one I work in for now, we use the hard copies of graphs and manuals and tables rather, to determine lots of aspects that have to do with the performance of calculations of the aircraft. And in other airlines, they will be using the EFBs, electronic means of just inputting data that is needed in order to automatically calculate the takeoff weights and the like. So in this presentation, we will not discuss on V speeds for this part. It will be discussed on part number 2. So let's see with an example. I'm going to give an example here. I'd like you to note this down quickly. If you have a pen and a paper, you can just note these details down for the airport that we're going to discuss. We're going to talk of Lilongwe, which is in Malawi, in the southeast African continent side. The elevation is 4,029 feet. Runway is 14, which you're going to use. The outside air temperature for this given day is 25 degrees. The actual takeoff weight as per our load sheet will be 27,600 kilograms. We're going to be using flap 5 for takeoff, and the bleeds and the de-icing systems will be off. So I'd like you to note this down. If you can pause the video, note it down, and then we'll continue from there onwards. Okay, so at least you know, because it won't become this information won't be repeating in the subsequent slides. So just make sure that you have this somewhere to refer to as we go through now how to calculate what we can carry, how much we can carry, and the like. Okay, assuming that you've done that, now we can continue. So the first graph that we'll refer to is from the AFM, the Airplane Flight Manual, and this graph gives you the maximum permissible takeoff weight. WAT stands for weight, altitude, and temperature limit, and for takeoff flap 5. And similar tables are there for flap 10 and flap 15 takeoff as well, but we're going to use flap 5. Now these graphs, which are in the AFM, are very, very much typical and similar to the ones we study at flight school when we are calculating performance for the Cessnas and the like, which you might recall, where you draw lines and then you interpolate and the like. Okay, so now here's what it is. We need to know that at a temperature of 25 degrees, and the pressure altitude of Lilongwe is 4,000. So you can see that the 4,000 line is this one here. You can see that the line extends to the structural limit line, and then it continues all the way. So what does this tell you? It tells you that at the condition given, you can carry more than the structural limit weight. That's what it means. However, being more practical, you can't do that. Okay, but there is no limit to how much you can carry in this case at this temperature, at this pressure altitude. But if you now start seeing where the maximum structural weight or the structural weight limit will be intersecting the pressure altitude line, will be somewhere there. Okay, and this is somewhere in the 30, let's say 36, 37 degrees. So from 37 degrees, okay, you can see that if you go towards the right from 37 degrees, now the maximum weight that you can carry will be less than the structural weight. So let's say, for example, where the cursor is here, okay, if you draw the line, it will be 29,000 kilograms, and so on and so forth. Okay, so it's very important to relate how much you can carry, and that also depends on the pressure, altitude, and the temperature. Very important. That's what it means by WAT. So for our condition of 25 degrees, we don't have any limit here on how much you can carry. But when that is the case, always remember the maximum intake is a structural limit weight. You cannot go more than that. So you cannot say, okay, I'm going to go to 31,000 and so on and so forth. You can't do that. The maximum you can take in this sort of situation will be the maximum structural limit weight. Okay, it's called the AFM limit. All right, so that's very important that you understand that concept. Okay, so just like what I've said, at 25 degrees up to around 37 degrees, we can carry more than the structural mass. All right, and this is not practical, as I've just said. So anytime we find we can carry any mass more than the structural, we limit our maximum mass to the structural limit, which on the graph, if you go back to it, is 29,600 kilograms. Okay, so that part is done. So the maximum weight we can carry is 29,600 kilograms. But remember, our weight is way more or less than that. So it means that we are quite okay. So beyond 37 degrees, as I've just said, if you go back to the chart, the maximum we can carry now reduces. And that you can actually see when you draw the lines. All right, now, the next thing, once we've dealt with the graph, okay, the AFM, from the AFM rather, we now come to this performance tables. It's a book on its own as well, okay, can be in soft copy as well or hard copy. And for every airport, there are going to be 2 pages for each runway. So if you look at this, for runway 14 in Lilongwe, all right, we've got 2 pages. The first page is basically the procedures. It gives you the procedure on top here of for the engine out procedures, all right, which you can discuss later in other videos where we talk of single engine operations. And then we've got a bleeds on table, then a bleeds off table with a dry end top, wet end top for bleeds on. We've got dry M top and wet M top for bleeds off. Then we've got bleeds off for end top on a dry surface, and also for tailwinds which are more than 10 knots. And on this table you don't only have that much, but you also have a column, 2 columns, one for temperature and one for torque that we're going to be using. And the other page will be for the same bleeds off this time, but it will be for a couple of configurations and the like, where is what we can see. So how do we use these tables? Here's what we do. I want you to pay attention very carefully. The first part of the tables that are given for the particular runway that we use will be this part here, which is on the second page, where it says dry end top. We are going to use a normal takeoff power end top, not maximum takeoff power M top. Okay, that's the first column we'll use. Okay, and I'll take you through the steps that are needed. After this, what we're going to use is this table here on the previous page, which will be the NTOP for dry conditions. Okay, if there were tailwinds of more than 10 knots, we would have catered for that, but in this case we don't. So this table serves for two purposes: NTOP for dry conditions and also tailwinds more than 10 knots. Okay, so we're going to use this table, and here what we're going to use, this part here. Okay, so make sure you remember those steps. All right, the dry NTOP, and then the NTOP dry, and then on the NTOP dry we're going to use the two columns, one for the temperature, outside the temperature, and also for the torque. Now let's see with our example what we do. So here we go. For the dry NTOP portion of the table, okay, for the long runway 14, we need to first of all find out that at our temperature of 25 degrees, how much weight or mass we can carry. If you can see, the temperatures are given here and the masses are given here. We will not take into account of a tailwind, the headwind. We'll just take the 0. So it will be just like a calm condition for now. Okay, but make sure that you remember that. So these are the weights or the masses we can carry. The letters here, the C's and the A's, and the numbers that follow them, 31, 32, and so on and so forth, these we'll discuss them in the second part. Okay, the C's and the A's are limit weights. I'll explain to you later if you don't have it already on your systems. And these are the speeds, but we won't touch on these one right now. Our main focus for this presentation is basically to work out how much we can carry, what is our maximum mass we can carry, and how to reduce the torque. So you can reduce the takeoff power simply for accommodating the engine lives. Okay, so 25 degrees is basically here, between 24 and 26. I hope you agree with me on that one. 24, it will be in here. Okay, it's not on the column itself, but 25 is between 24 and 26. Fine. So now what we have to do, we have to find how much mass we can carry for 25 degrees. And since for 24 degrees is this value here, and for 26 degrees this value there, we can comfortably say that the value for 25 degrees would be somewhere around the same values, 29,570. That's how you read this, right? You can see it's only given 4 digits, but always add the 0 at the end. So for instance, this was 28,730, and this was 29,310, and so on and so forth. So this is 29,570. Okay, and what we do now, the maximum takeoff weight we can carry is 29,570 kilograms. Okay, because you can see that doesn't change all the way down. All right. Reason being is that this airfield is pretty much on the lower side, so as temperatures are getting less and less and less, we can carry approximately equal to the maximum certified weight of the aircraft. Okay, so that's the reason. And as temperatures increase, as you can appreciate, the higher the temperature, the less the weight you've got to carry for performance reasons. Okay, that's good. So then what we do after that is this: we locate the temperature and then its corresponding weight or mass we can carry, and then we move upwards on this column until we find the closest value but the highest to our actual takeoff weight. I will repeat once more. You locate the temperature, outside the temperature, on that particular day. You find how much weight you can carry for that temperature. Then you start moving upwards along this line until you find the weight value that is closest but the highest to the actual, not this one here, but the actual, which it means that it is going to be a load sheet figure. Okay, so load sheet figure was 27,600 kilograms, and if you look at the values here, the next closest and highest to 27,600 kilograms is 28,730 kilograms, which is right at the top here. Okay, once you've located that, then the next thing you want is to note it down as we've just done, and then you want to work out, or determine rather, to what temperature does this figure relate to. Okay, so 28,730 kilograms corresponds to 40 degrees. Okay, so it means that if the ambient temperature was 40 degrees, you could only have carried this much. But since your temperature is 25 degrees, which is way lower than 40 degrees, you can carry 29,570. I hope that's making sense. Okay, so now what we do, what's the whole purpose of this? The whole purpose of this is to use assumed temperature method. And the assumed temperature method simply means that you want to tell the aircraft that, listen, outside it's not 25, it is 40. You are assuming it. So you're going to program your aircraft to work as though it's working in a 40-degree environment, but actually it's not. And the reason why we do that is that the higher the temperature, the lesser the torque. So you are going to reduce the engine wear and tear if you do that. There is that method we use for the Dash 8 Q400 and other turboprops, I think. Then there's something called derated takeoff for the jets, okay, which is not a subject of this presentation, but derate takeoff and assumed temperature method takeoff are all there to just save engine life. Okay, so make sure that you remember these. Okay, so having said that, now with the assumed temperature in our case will be at 40 degrees. Okay, and at that particular temperature, it tells us that we can carry 28,730 kilograms. Okay, excellent. So now what we can do, we now go to this table here, which I said that's going to be the next step. And in this table, we are not going to focus on all this jargon here on masses and speeds. We are going to be focused on this bracketed part here, which I actually told you in the previous slides. So again, 25 degrees is between 26 and 24, 26, okay, which is somewhere that's 25 degrees. Okay, so the torque for 24 degrees is this one here, and the torque for 26 degrees is this one there, which means that the torque of 25 will be in between the two. So we are going to show here how we can use the method of interpolation. There are many methods for interpolation that people use. I'm going to use one of them here and hope that it might make sense to you. So here's what we do to interpolate. Okay, we are going to interpolate between these two figures and those two figures. So we know 25 already, but we have to get the torque that corresponds to 25. And to do that, here's what we do. The first thing you do is that you take the known figure, the one which you want to work out the other value for, which is 25 in our case, and you find the difference between it and the lowest value. Okay, and you find the difference between the two end values. So 25 minus 24 divided by 26 minus 24. That's going to give you a half. Good. And then what you do, you're going to find the difference between the two known values for corresponding to the 26 and 24 degrees, which are 89.3 and 87.7. And you're going to multiply what you got here, the half, by that difference, and you get here 0.8. Okay. And then what you can do with that 0.8 is very simple, because you can see that from 87.7 going downwards you are increasing, so you will add. So 87.7 plus 0.8, you're going to get 88.5. So which means that 88.5 is the torque corresponding to 25 degrees, right? Now you must remember that the aircraft doesn't give decimals on the ED when you start pressing the N top or M top or the reduce takeoff power button, right? It doesn't give you decimals, it gives you whole numbers. So 88.5 will be 89%. And you can clearly see that is somewhere around 89% here, and then it keeps increasing. Okay, so this 89%, I'd like you to note it down, is the torque that corresponds to our actual takeoff weight. The torque that corresponds to our actual takeoff weight. You'll see why we are using these terms in emphasis. Okay, good. So now we've worked out the torque for 89%. What's the next step? Let's look at the excerpt from the performance handbook. a lot of reading here, but I've just highlighted the main points that I'd like us to focus on in order to calculate our proper torque and our proper weight values. Okay, so here it says in the first paragraph, the minimum torque for the assumed outside air temperature is 0.9 times a normal takeoff power setting. Okay, so this normal takeoff power setting, we're going to get it from a table from the AOM, which is coming in the subsequent slides, which you will see. This is for you to read when we can use the reduced thrust takeoff. And then it says here, to obtain a reduced power setting, find the weight that is nearest to but greater than or equal to your actual takeoff weight in the applicable max weight limit code max V1 column. That's what I told you. You remember we had 27,600 kilograms, then we went upwards to find the closest and the highest value of that one. Okay, you can even review, you can go backwards and you can see what I mean by that. Okay, and then that's very important. Now, if the torque setting that corresponds to the actual takeoff weight is greater than or equal to 0.9 times normal takeoff power setting, then the reduced power can be used. So how do you know whether we can reduce or not? This is the lines that you've got to abide by. So I'd like you to keep this some way, or make it, maybe take a screenshot of it, or take a picture of it, because you'll see we'll be using this to determine if we can or we can't reduce. Okay, I'm hoping this is making a bit of sense for now. So we continue, and here is the table for the normal takeoff power settings. Okay, NTOP. This is from the AOM, and at the bottom here, as per our condition, ice system in our case is off and the bleeds are off. Okay, so we are going to look at that. Now let's see what we can get from this one to now find the NTOP torque. Remember, the first one we found was the actual torque for our actual conditions. Okay, actual takeoff weight. Now we're going to find the NTOP torque. So to find the NTOP torque, we look at the temperature. Again, it's between 26 and 25 degrees, somewhere there. Okay, and then we look at the pressure altitude of the Lilongwe Airport, which is around 4,000 feet, which is that one there. So we are concerned with this column here. Okay, and the torque value should be in between these two values here, which will be 7.5, 89.1. Now let's work that out using interpolation. So again, I've just done this for you based on the same concept I taught you about how I interpolate using sets of values. So if this makes sense to you, all good and well, which means that the NTOP torque is 88%, and you clearly see it should be around 88% here, because you are increasing as we go down. So 87.5 might have 88%. Okay, so this is our NTOP torque. Now what does this mean? 0.9 times the NTOP torque is 79%. 0.9 times 88% is 79%. So now we can see that our actual takeoff weight torque, which is 89%, is greater than this one. Okay, and if you remember from the conditions in the excerpt, if this is the case, it tells us that yes, we can reduce. All right, so now let's look at that and see what the reduction means. So here it is. This is our actual takeoff weight torque, which you worked out. Yeah, so then we start pushing the RDC TOP switch on the engine panel of the dash 8. Okay, and every push, if you recall from your AOM, gives you a 2% reduction in the torque. Yeah, 2% reduction. So every time you push, you're reducing by 2. So this is going to be your first push, 87%, 89 minus 3, 87. Your second push will be 85. Your third push will be 83. And your fourth push will be 81. And then your last push will be 79. So you can always go to 5 times. That's your limit, right? That's what you know. It's a maximum reduction is 10. And you clearly see that you can go all the way there. But now, if you look at the torque value for 40 degrees, okay, from the NTOP dry table that we looked at, you would have seen that the torque value was 75%. You can visit it again. You can go backwards and just make sure that you know what I'm talking about here. It was 74 point something percent by 75%. So this one basically is your assumed temperature torque. Now you can see that your assumed temperature torque is less than the 5 pushes that you've made. Okay, it's less than the last push, which is 9%. And when that's the case, you can only do until 5 times. All right, just remember that. And there will be a summary towards the end which will tell you what I mean. Okay, so if the torque that corresponds to the assumed temperature is less than the 5th push torque, if I can put it that way, then you can go until 5 times. Otherwise, you just stop to where your push value on the switch matches your assumed temperature value torque. Okay, I hope this is making sense for now. So assuming that, we continue with another example. Okay, so that one was done now for Lilongwe. Now let's do another example, and this is going to be for Harare. So here again, I'd like you to make notes of this. The airport we're looking at is Harare. The elevation is 4,901 feet, which is approximately 5,000 feet. Runway news is 05. This time it's quite hot out there. Outside the temperature is 36 degrees. We're going to use the same takeoff weight, actual 27,600 kilograms. Flaps we use 5, and again bleeds and de-icing will be off. Please make note of this or pause the video, and once you've made note, and then we can continue. Alright, so again we go to this table of hours as we did in the previous example. Alright, and we locate 36 degrees, which is there. 36 degrees is there. Okay, and then we draw a line through 36 degrees vertically upwards so that it hits or connects with the pressure altitude line for the airfield, which in our case is roughly 5,000. We use easy figures to deal with, 5,000. And when we do that, we reach this point here, and from there we draw a straight line horizontally to read out our maximum takeoff weight we can take on this particular day. That's 28,600 kilograms. So 28,600 kilograms is our maximum takeoff weight on this particular day with these particular conditions. Okay, excellent. And remember, our weight is still less than this one. So we can take up where we are comfortable to take up to this. You remember the Lilongwe one, we just shot all the way up, but here now we can't, our maximum isn't the structural limit maximum. It is something else, because that's where the AFM is telling us to stop our calculations. Okay, good. So now again, it's same procedure. We are repeating the same procedure. As I said, that for every airport on the performance handbook, you will be given 2 pages for each runway. Okay, and here are the 2 pages for runway 05 in Harare. Okay, and what are we going to look at? We're going to look at this column again for dry end top, for bleeds off. Okay, and thereafter, once we are done with that, we're going to come to this table here. Okay, and on this table we are going to be focused on these 2 columns. Can you see that? It's 1, 2, 3, right? There are 3 things that you've got to do. All right, so using the same concept that I hope you're taking notes as I was going through, but maybe you'll play the video again as many times and you can make notes as we go along. All right, so here's what we're going to do now. Let's get the bleeds off, dry end top part separate. So again, the temperature in this case was how much? 36 degrees. And at 36 degrees, how much weight can I carry on this flight? I can carry 28,750 kilograms. That's at 36 degrees. Okay, excellent. But remember that our actual takeoff weight was 27,600 kilograms. So what's the rule again from the excerpt I showed you, and what I did before I even showed you the excerpt, is that you find the closest but the highest to our actual takeoff weight, which is 27,640 kilograms. Excellent. And then the last thing you'll do here, as you might have correctly guessed, we have to work out the temperature that corresponds to this weight, and that temperature is 40 degrees. Okay, so that's going to be our assumed temperature again. All right, that's assumed temperature. It means that we can assume a 40-degree environment outside. In actual fact, it's just 36, it's 4 degrees less. Okay, but the whole point, once again, to repeat, is to save engine life. We are fooling the engines, all right, literally, to tell them that, hey, the outside air temperature is quite hot, but in actual fact it isn't. Okay, good, very nice. So then we go to our other table for the dry end top for bleeds off, and let's look at this. For 36 degrees, the torque will be around 76%. This is the value. 75.7 is roughly 76%. Okay, the assumed temperature torque, as you can see, is going to be 72%. Okay, that's going to be that one there. Very good. Now you can clearly see that we've already got our actual takeoff weight torque. Okay, now we want to find the end top torque. You see, that's how we compare. Remember, that's what we do to compare if we can reduce or not. So for our end top torque determination, first of all, look at the column which is relevant to us, which is the 5,000 foot column, which is the pressure altitude for Harare. There it is. Good. 36 degrees is exactly here. So this time is a proper value, no interpolation needed. And the end top torque is 75%. Very good. Now let's do some calculations to determine if we can reduce or we can't reduce. So again, the actual takeoff torque was 76%. The 0.9 times the end top torque will be 0.9 times 75, which is 68%. And here clearly you can again see that the actual takeoff torque is greater than the 0.9 times end top torque. And when that is when that condition is satisfied, it tells us we can reduce the power. We can fool the engines to say you'll not perform at our actual takeoff weight torque, you'll perform at a lesser one. Now we determine how many times are we going to reduce, okay, or how many times are we going to push the RDCTOP switch light. And to do that, we start with our actual takeoff weight torque, which will be displayed on the ED, 76%, okay, and then we're going to push, let's see how many times. The first push is going to give me a 2% reduction, which is 74, and another 2% will give me 72%. Now can you see that 72% is the assumed temperature torque that we talked about in the previous slide, okay, for this particular configuration. Now since we have already reached that value in our pushes, okay, it means that we're going to push in this case only twice, so we're going to reduce twice. Okay, instead of 76% performance, we are going to use 72% performance. Okay, that's I hope making sense. All right, so having said that, this is going to be the rules that I want to show you. If the assumed temperature takeoff torque is less than the actual takeoff torque minus 10 meaning you can only push 10 times, you're going to go ahead and do 5 pushes on the switch. If the assumed temperature takeoff torque is more than the actual takeoff weight torque minus 10 again, this time you will push until you get the assumed temperature torque. This is very important. I'd like you to make sense of this and make sure you understand. And please, for those of you who are way more informed in this concept of working out the torques and the assumed temperatures and the associated weights, if there's anything I have missed, please make comments, please make constructive comments. It's all for the better of educating others. If I've made a mistake or if I've explained something which isn't making sense, but you guys might have other ideas or other knowledge, please do share. It'll be very worth it for the future generations who are going to be using these platforms and these resources. Okay, so what we're going to do that in part 2, the discussions will be on the various performance limit weights and calculating V speeds manually, which will come in due course. And for now, all I can say is that be safe. You guys have happy flights. Please comment, contribute to this channel, so at least we can inform everybody in the aviation family on what we actually do on the flight deck. And for those of us who are actually flying the Dash 8 Q400, please, if you have any further suggestions and other knowledge you can share, yeah, it will be way more than welcomed, way more than welcomed. Okay, until the next time, wishing you safe skies, and you will see me again, well, you'll hear me again rather, on my other presentation to do with the same topic we are on right now. Okay, go well, and God bless you all. Thank you.